Okay, so we finished our the last lecture by talking about what the F statistic is, right? And we said that it was basically the ratio of the variance due to the intervention or the manipulation of the treatment. Basically, those are all the same thing over variance due to error, right? And this makes sense, right? We've been talking about the idea that if the variance due to treatment is equivalent to the variance due to the error, then it would basically say that essentially all the variability in the sample is due to random experimental error and has nothing to do with the treatment intervention. So not surprisingly, then the F statistic would be statistically non-significant. And then we ended by talking about the fact that, like the t distribution, the F distribution is not a single curve, but rather a family of curves. And the shape of those curves change as a result of the sample size, which is the same as the t-test, but it also varies as a function of the number of groups included in the test, right? So that's another way in which ANOVA helps us to reduce the risk of type 1 error. All right, so because of the fact that the F statistic curves change as a function of both sample size and group size, we need to calculate some different degrees of freedom in order to be able to identify what our F critical value is. Now, because we're going to be using SPSS, when we use SPSS, we're not going to have to worry so much about that, but it's important for you guys to know how to calculate degrees of freedom. So, okay. Remember, we mentioned there are two different types of variability. We have the within treatment variability and the between treatment variability. So we have different degrees of freedom associated with both of those types of variability. So our within treatment degrees of freedom is going to be, the notation will be df within. And that's going to be equal to n minus k, where n is the total sample size. So across all of the groups, the total number of people included in the study, and k is the number of groups, the levels of the independent variables. So in an ANOVA with a sample of 100 and 3 different groups, n would be 100, k would be 3, and our within treatment degrees of freedom would then be 97. Right? 100 minus 3 is 97. We also have degrees of freedom associated with our between treatment variability, and in this case, it is k, the number of groups, minus 1. So in that same example, we would have 3 minus 1, which would give us 2. So when we think about the degrees of freedom associated with an analysis of variance, it's going to be 2 and 97. Now, our total degrees of freedom is going to be the total sample size minus 1. So that should be 100 minus 1 or 99. But we should also see that our within treatment and our between treatment degrees of freedom, if added up, will be equal to our total degrees of freedom. So in this case, we had within treatment degrees of freedom associated or was 97. Our between treatment degrees of freedom was 2, which gives us a total degrees of freedom of 99. Okay. All right. So as with t-test and any other test, there's certain assumptions that have to be met, and many of them are the same. So independent and random sampling from the population, right? So we want to try and get as representative of a sample of the population as we possibly can. And each one of the individuals that we're including in this analysis are going to be independent of one another. They're each going to only supply a single data point. Now, there are ways in which we can do within subjects designs with ANOVA, kind of like our paired samples t-test, but that's beyond the scope of our discussion right now. We have a dependent variable that's measured on an interval or ratio scale, again, same as the t-test. And our dependent variable is normally distributed. Again, same as the t-test. And then finally, equivalent to the independent samples t-test, we need to have homogeneity of variance of our dependent variable. So in other words, the variance for the dependent variable within the 3 treatment groups has to be the same. And the reason for that is the same as for the independent samples t-test, because we're essentially going to be looking at the average variance across the 3 different groups, right? So you don't want to average them if for some reason there's greater variability in one group than there is in another. Okay. And again, we would say that ANOVA is pretty robust against violations of these assumptions, but the degree to which we can meet them as closely as possible is going to be critical, right? So it doesn't have to be perfect, but it should be close. Okay, so hypothesis testing. Here we're going to look at comparing the null versus the alternative. This is a non-directional hypothesis. So in this case, we would be using what I call post hoc tests, right, where we're not making specific hypotheses about differences between specific groups. So, but in that case, our null hypothesis would be that mu1 equals mu2 equals mu3 up to mu k, where k is our number of groups. Right, and I told you before, infinite number of possibilities. Only limitation is our sample size and money. Our alternative hypothesis then for a non-directional test would be some mu's are not equal. Now remember, I also said there was only one-tailed tests, so it doesn't really matter if your test is directional or non-directional because we're going to be doing other things to ensure that we reduce the risk of one type 1 error. So if you think about it, right, splitting alpha and making our critical values higher for a non-directional test is the way in which t-tests reduce the risk of type 1 error, right? So in the case of ANOVA, it essentially, we've already explained how that works, right? So I'm not going to go into that again. The other thing that you need to know about are the effect sizes for the F statistics. So we've been talking about Cohen's d, which is expressing the magnitude of the difference between groups in standard deviation units. Our effect size for the F statistic is actually different. It's called eta squared, and this is how it is represented, the Greek letter eta squared. And what eta squared does is estimates the amount of variation in the scores that is due to the manipulation or the treatment. Okay, so the amount of variation in the scores that's due to the manipulation of the treatment. So just what that actually means then, what that actually means then is imagine, for example, that this is a pie, and this pie represents all the variation in our outcome. So let's just assume, for example, that our outcome is final exam scores, okay? And we can argue that final exam scores are going to have quite a bit of variability, right? Some people are going to study and do really well, and then maybe they'll get 100%, and some people are not going to study and they're going to do really poorly, and they're going to get, say, 50%, and then you're going to have people in the middle, some who kind of got the material, but didn't study that hard, maybe they got an 80%, so on and so forth, right? So we would expect that there's going to be quite a bit of variation among each of the individuals who took the test in terms of their test scores. So one of the things that we want to find out is to what extent or what percentage of that variation in test scores can be explained by our independent variable, right? So in this case, we can think of our studying might be our independent variable, right? And eta squared is going to give us an estimate of what percentage of the variation, right? If this is 100% of the variation, what percentage of the variation can be explained by knowing how many hours the person studied. So just for grins, for example, to give you kind of an example of this, imagine for a moment that I lined you all up in height order, and I wanted to sort of be able to make a prediction about your same gender parent's height. And let's just say for grins that 25% of the variation in your parent's height is associated with or explained by your knowing your height, okay? So what that actually means is that about 1 in 4 times, based on knowing your height, I could accurately predict your parent's height. So, okay, but so what does that mean in terms of this 25%, right? What is 25% really in the scheme of things? Well, what it really means is that 1/4 of your height is predictable, or your parent's height is predictable based on knowing your height, but another 75% of your parent's height is due to other influences. So we could say that it is due to, well, obviously some of your height is going to be due to your opposite gender parent's height, right? So if you have a really tall parent and a really short parent, your height may kind of average out, in which case you're going to the prediction of your parent's height is going to be less accurate. With your same gender parent's height is going to be less accurate without knowing your opposite gender parent's height. Another factor might be your parents' nutrition, right? So maybe they grew up and didn't eat as well as you did, and so their height is going to be affected by that. All right, so what this is saying is that we're going to get roughly about, a 25% accuracy in prediction based on knowing this one variable. But 75% of the variation is going to be due to other things that we haven't accounted for yet, including error, and that's going to reduce the accuracy of our prediction, right? So the more independent variables that we include in our model, the more variation we can explain and the more accurate we would be in making those kinds of predictions. So that's really what eta squared is telling us, is what percentage of the variation in our outcome measure can be explained by knowing the person standing on our independent measure, right? So in this case, it might be what percentage of the variation in scores is actually due to our experimental manipulation. And eta squared is calculated by comparing the sum of squares for the between groups variance, right, which is essentially the variability due to the treatment, and it's a ratio of that to the total amount of variation in the group. And that kind of makes sense, right? So anyway, that's what our effect size estimate is actually going to tell us.